what I'm doing here, where I'm pointing. So I've just popped this glorious autumnal photo up. So for a lot of our growers, this is the reality of autumn. And I don't know about you guys, but when I look at that, yeah, I'm a bad veggie gardener, but when I look at that, I don't think, this looks perfect to plant some seeds and get some plants up. But this is the reality that a lot of growers face in autumn. And obviously, for anyone that works in the grains industry, dry sowing has become a management practice. It's been uptake across Australia hugely in the last 10 to 15 years. But what I'm going to be talking about and what we've been working on is on this, that in a paddock like this, more often than not in autumn, if you dig down 50, 100 mils, there actually is soil moisture sitting there under that dry layer of soil at the top. And so what I'm going to be talking about is some of the background science behind deep sowing, but then also about a project that I ran that finished mid this year. It was a Future Drought funded project looking at the fit for deep sowing for helping on-farm resilience under changing rainfalls, which is something that so many people are experiencing on the ground. So what scenarios are going to benefit from deeper sowing? Where is this mystical water that I'm talking about? Is it actually there? You know, when you look at it, a dry paddock, it's hard to see. And so the fit for deeper sowing in a climate scenario is generally around moisture seeking. So it is looking for that moisture. And this is due to changes in the season break, so those first rainfall events in autumn, or patchy breaks. So instead of the classic big opening rains and then winter has started, or when you get the beautiful opening rains, but as has happened a couple of times in the last 5 years here in WA, you then have 4 to 8 weeks of hot, dry weather, which if you've got a large sowing program, you know, it's a bit meaningless. You can't get it all into the moisture. So I've got a couple of maps up here. You know, I'm kind of preaching to the converted, but for a lot of people, the context of changing rainfall patterns just in autumn isn't something they're so familiar with. So the top maps there is looking at the season break. So this is those first autumn rains. And you can see basically, it's all pretty small, but basically the darker the brown is, the later the break is coming. As you can see, post-2000, there's a lot more dark brown. And those two darkest browns mean that the median break is actually occurring in June. That's really late if you're a grower wanting to get lines in, and it means you're having to put really short, like fast developing lines in. And down the bottom, this is all happening in the context. It's not just season break, but it's also happening in the context of rainfall changes, and that's reduced autumn rainfall. So in the lower graph, the 1991 to 2020 graph, the lighter the colour it is, the less autumn rainfall. So that's that March, April, May rainfall. And I think this is important because in a lot of these areas, annual rainfall might not actually be shifting, but it's actually just that pattern of rainfall that's shifting. And for growers who are reliant on that for rain-fed agriculture, particularly in that early stage, because seedlings are far less resilient. Once a wheat plant's established, it's tough as, but in those early stages, it's not, and you need that moisture to get germination happening. And this is important for growers trying to get timely crops up. So dry sowing is great, but you're still reliant on that rain to actually get those crops up. And this is also a real benefit for non-wetting sands, which is something that we experience across Australia, because often in those you'll find, particularly in these lower patchier rainfalls, it just doesn't infiltrate in. Slightly less on the climate context, but still important, is deeper sowing is also great if you've got furrow infill, which if you have had rainfall, got it in, and then it's all dried out and a massive windstorm comes through, is something that's often experienced by growers, or in ameliorated soils, which in Western Australia is half of the wheat belt. If you're sowing onto soft sands, often depth control can be pretty hard. So this all sounds great, but what can you actually sow deeper than 50 millimetres? Pretty much all the pulses, not your lupins, but most of the other pulsins without any need for genetics, breeding, anything, you can just go in deeper than 50. Oats, and you watch this space, there was an amazing master's student that did some great work over the last couple of years, and now Facey Group with Intergrain are on a GRDC funded project looking at oats and putting oats in at depth, because they're a great fit for that early season growth, and long coleoptile wheats. And so it was in this context that I started the Future Drought Fund, that I got the Future Drought funding. And it was kind of going, we have all this knowledge, people are keen, but where do we go? And so we started doing some investigating about where the knowledge holes were, and we were really surprised. Everyone was excited about long coleoptile wheats. No one actually even knew what a coleoptile was once you actually got out there. So I'm going to take you on a little scientific journey, because it's actually the science that underpins all of this, which is so important. and it's what you needed. It was an extension-based project, but a lot of the extension was actually joining that passion that we had from all the growers to the science that we already knew. So in simplest forms, a coleoptile is just a little protective sheath that goes over the first leaf on a cereal. So you can see here when it grows, you get the coleoptile. These are some wheat in the field. And basically your first leaf's not very strong, and so as it's elongating up through the soil, you've got this nice protective sheath that makes its life easy. And once it gets into the light, it's got through the soil, the first leaf breaks through, you're happy. Obviously, if you've sown your plant really deep, that's going to be a little bit more complex, and that's where you need these longer coleoptiles to allow that to get through. And you can see, I don't have a pointer, do you? You can see over there that there's a large variety in the coleoptile length that you're finding in modern wheats. And so what impacts coleoptiles, and why is this even something that we're interested in? And the reason we're interested in it is because of the green revolution, which you may have learned about at uni. If you work in grains, you'll be more familiar with. And basically this is when we took these big, tall, floppy wheats back in the day, and we started working out that we could shrink them right down, so you had these small, compact wheats, you got these huge yield gains. Everyone was really pumped. But what we didn't realise was that those shortening of the shoots also was leading to a shortening of the coleoptile. But it made no difference, because at the time, it didn't really matter. Most people by then weren't even sowing by the calendar. They weren't dry sowing. The break was coming. You know, it was an Anzac Day. Everyone got out there, started sowing. It was beautiful. Fortunately for us, there's a whole bunch of alternate dwarfing genes that give us the same benefits of small stature crops, but they don't reduce the length of the coleoptile. And so anyone that's worked in the grain space, long coleoptiles have just been, it's a word that's been thrown around so much in the last few years. And often people talk about lines, they'll be like, oh, it's a MACE 18, it's a this. And most people have no idea what it means. It's just talking about what dwarfing gene is in that line. As you can see here, a standard MACE with short coleoptiles, and on the other side, it's a near-isogenic line. It's exactly the same. It just has this different dwarfing gene, and it's got the long coleoptile, so you can sow it deep. The other thing that affects it is temperature. And you may be wondering why on earth I'm talking about this. It's not a science talk, but it fits into the system, because if you're going to sow plants and chase moisture, usually for farmers, that means they're trying to sow them earlier. If it's earlier in autumn, it's a lot warmer. This is showing coleoptile lengths at 15 degrees. If you measure them at 20 degrees, they're so much shorter. And so that interplay between temperature and the genetics is integral to get the varieties out there for farmers who are wanting to use deeper sowing to chase moisture, chase that summer stored moisture or from early rainfall events, and actually get crops up from deep. So with that little bit of background, so you understand what I'm talking about, hopefully, when it comes to these long coleoptile wheats, I'm going to talk about the sowing trials I ran as part of the Future Drought Fund. It was a really extension-based project. And part of it came from the idea that we'd been doing all this research about the background and the genetics and all the impacts on of these long coleoptile wheats. And when we talked to growers, there was so much passion out there and interest in whether they could integrate this as a management technique on their farms. But we were working with breeding lines. Everything we were working with was totally unavailable to the actual grower who's out there. And so the project came to actually look at, if you were a grower wanting to plant something deep or experiment with it, what was actually out there that you could use? So we went through like every line that we could find. Some breeders are starting to like release lines that were out there. We got all of them, and we ran national trials. We had 11 trials nationally. We had pulses at some of the trials where there was an interest from the grower groups and the growers in that region, and to look at shallow and deep sowing, what's available commercially, how does it perform in your area, and what's going to happen. And then we had some other treatments that people were interested in on some of the trials. And so I'm going to present a tiny bit of data. The idea is not to haze you all at this time of day with a bunch of graphs, but it's more just to give you a vibe for what kind of data we're getting and how impressive this management technique is in terms of drought resilience. I'm using the West Australian sites because we're here in WA. Here's Narrogin. These are emergent, so how many plants have come out 6 weeks after sowing. They're just different types of wheat. And the light green is shallow, the dark green is deep. Obviously, deep has not come up as much, and this is one of the huge parts of the extension project was about the fact that deep sowing isn't something we think everyone should be doing all the time. It's a tool to have in your toolkit. It's a management technique to use when you need it. But what you can see is those longer coleoptile lines were actually emerging at 60-70% of those of those short, shallow sown lines. Minganoo, slightly different. You can see that there's far higher emergence of those deep sown lines, those dark bars, but that's because it is cooler. And that's this interplay about time of sowing and those coleoptiles and how it's all part of this system that needs to work in different locations for growers. Yield is obviously God. The main thing that we found here was that these lines were yielding, even if they only had 70% emergence of their shallow lots, they were yielding at the same rates. And for growers, this is what's exciting, this is what's interesting. But these trials were also on into moisture. It's not a time that you would normally be recommending deep sowing. If you've got moisture of 3 centimetres, why would you sow deeper? So I just wanted to give a quick example of a South Australian trial, which was a non-wetting soil, where the deep ones went into moisture. So you can see the dark bars, 110 millimetres, and they emerged far faster and far more, and to a far greater extent than those that went into dry soil. So the shallow soil ones, it was only 2% soil moisture. Those deep ones were at 7% soil moisture. And so this is the example, and this is an example that we had in this season here in Western Australia, where we got those amazing early breaking rains, where for a lot of growers, they actually could get into moisture early. I realise that I have put up, this is more the conclusions I put up when I'm talking to growers, but I think that that's not actually a bad thing for this audience, because the main thing that came out of this project was the ability to actually have so much extension work. We ran numerous field walks, we went to numerous field days, and it was this huge opportunity to get an understanding that for growers, deep sowing is something that everyone's really excited about. People want a trial, but they need a solid understanding of the science behind it, the agronomy behind it, and how it's going to work. I think that deep sowing is something that's going to have a huge uptake as rainfall patterns change, and it's a massive, it could be a massive tool in terms of a management strategy, but there needs to be an understanding. Obviously for a grower, there's a huge risk and a potential cost if they take on a management strategy like this without a full understanding of it. But I also was amazed at how many growers were already messing around with this as a technology, particularly with their pulses, which they felt more solid with, to actually just try out their gear and get it going. So it was a massive project. We involved a whole bunch of grower groups and breeding companies. So thanks to all of them. There was a lot of us involved. But I will wrap it up because I think we've only got a few minutes left. It looks like afternoon tea's next, so I'm sure everyone's keen for that.
Thanks, Sarah.